Guys, welcome back to the continuation of lectures on quantum field theory. This is again chapter 7, Feynman Rules, and this is part 2 of the said lecture. And along with this lecture, please read the books of Michio Kaku, F. Mandel, and G. Shou, and of course F. Gross. They're all in the topic of quantum field theory. Now we go to the basics of the Feynman rules. One of the difficulties of perturbative expansion is that it is the refinement of the calculation using corrections that are becoming smaller and smaller. The reduction is quantified by the power of the perturbation parameter, which is just the coupling strength. So at some point, adding refinements that are too small could be terminated, since they will no longer affect the final result, since they are negligible. In such perturbation expansion, the amplitude m for a given process can be computed using this summation. So you terminate at some point or at some part of the series as you reach some n. Each individual amplitude mn here is a specific particle reaction. It could be scattering or decay, and of course it's represented by a Feynman diagram. The higher the order of mn, the less likely it occurs and the less it contributes to the overall amplitude. The mn here have the same incoming and outgoing particles, but represent different intermediate states. The intermediate states correspond to the terms in the Dyson series. For example, say this one, you have two particles going here, and so say A and B particles, and they just come out there. I'm sorry for that. Say this one and this one. This is C and D, for example. It could be that it could be this one. This is another M. So they have the same initial and final states, but of course the intermediate state is, or the reaction are different, so they represent different mn here, and they have this, of course, this one is higher order, so this contribute a little to the Dyson series. We note that each term mn is scaled by a coupling constant g, which represents the strength of a given interaction. And as you go higher, as many vertices are produced in the intermediate state, the lesser it contributes, because g there is supposed to be very small, and when you have a lot of vertices, you have to raise it with the number of vertices, so it becomes smaller. So when the relative strength of a given interaction is small, then it can be analyzed using perturbation theory. A Feynman diagram, by the way, we're now talking about Feynman diagram, consists of one or more external lines that represent the incoming and outgoing particles, and they're connected by a vertex. So here you have to be you have to take note of the time, and the time can be taken to flow from the bottom to the top of the diagram, or from the left to the right. For example, if you imagine a particle decay involving particles A, B, and C that proceeds with A breaking up into particles B and C, so you can write it as this one, or you can write it as a Feynman diagram. So drawing the time going from bottom to top, the Feynman diagram is shown here. So you have A decaying into B and C. So may I just read the caption of Feynman diagram for the decay process A decaying into B and C. So if we could draw for the time moving from left to right, then we will have this diagram. So Feynman diagram for the decay A from A decaying into B and C. So in this case, time is moving left to right. So Feynman diagrams are qualitative symbolic representations of some interaction. Normally, the direction of time is not explicitly indicated on the diagram, and it should be understood from the context. Scattering events will involve an intermediate state or particle that is drawn in the diagram as an internal line. Suppose that A and B scatter with particles C and D leaving the process, and suppose that the scattering involves an intermediate particle I, then it can be represented by this Feynman diagram here. But usually this is not written. Sometimes you just put some arrow. Say for example, in this case you have this one here, or A going there and B going here, and it goes here, and then you have an arrow going there. Or it could be that it could be this, it could be this one, and then you have that one, and then you have this one and that one. So later on we will understand what the arrows mean. So here in this figure, You have AB interacting, it produces a particle I, and then I decays into C and D. But here in this case, your time is flowing from left to right, unlike the first one where your time flows from bottom to top. Particles can scatter via the exchange of a boson for scattering particle. And say for example, the scattering is this event. You have two particles scattering, interacting, and then they scatter and produces the same particles in the end. The particles C and D exchange a boson B during the scattering event, and this can be shown in this diagram. So you have particle C and then you have particle D. They interact with each other and then they scatter themselves. In this case, you have time flowing from the bottom to the top of the diagram. So particles C and D move in, then scatter by the exchange of the boson B, and then move off. So in quantum field theory, there are two types. You have particles and antiparticles, and the antiparticles also take part in many processes. So in this case, we have to indicate the labels for particles. Say for example A, and for antiparticles we have to put a tick or a prime, A prime. The lines for particles in a Feynman diagram are indicated by an arrow that flows with the direction of time. So for a particle, the arrow flows with the time, and then for antiparticles, the arrow is opposite with the direction of the flow of the time. So if we have a reaction A plus A prime interacting and producing A and A prime, where A scatters with the antiparticle A prime via the exchange of a boson, the reaction would be this one here. So you have a particle going in with the time and then an antiparticle going out opposite to time, but they are interacting and they exchange a boson and then they go out. But in this case, you have to put an arrow that's going here and going here. So in this case, you have the flow is opposite with the time here, opposite with the time, and here you have going with the time. So that's the scattering event of A plus A prime going to A plus A prime, using arrows flowing with time to indicate a particle and arrows flowing against the time to indicate an antiparticle. One of Feynman's brilliant observations was that a particle traveling forward in time is equivalent to an antiparticle traveling backward in time. This is why the arrows indicating an antiparticle is traveling backward in time. Now for this figure, you have A and A prime annihilating and producing a boson, and then that boson decays into an A and A prime. So this is another version of A plus A prime going to A plus A prime. But this figure is supposed to be A prime because it's against the time, and then you have here uh, an A here. You don't have to put the prime there. So that's another representation of the reaction A plus A prime going to A plus A prime, with the time flowing from left to right. Each line in the Feynman diagram is characterized by a 4 momentum, so it is useful to write momentum on each line. So suppose that you have again a scattering of A and A prime, producing A and A prime. And this one occurs with the exchange of boson, as shown in figure 7.6 earlier. So we indicate the momenta of each incoming and outgoing particle or external line with a P. So you have here a P, A with a for momentum P1 enters, and then also an antiparticle enters, but the for momentum direction is against the time. So they exchange a boson here, and then it goes out. Also, the A prime goes out with opposite momentum. But then again, P3 and P4, it's not P1 and P1, but you have to indicate you have to indicate a P3, because it doesn't necessarily mean that that momentum is conserved. However, you must know that P1, in this case P1, if you want to conserve the form momentum, this is P1 is equal to P3 plus Q. So that's the Feynman diagram showing the momenta. And now we're going to calculate the amplitude, which is very important, a very important quantity, because it measures how prominent the interaction would be. So the higher the amplitude is more prominent. So we will calculate the amplitude M, and to calculate that we have to integrate over all internal momenta. It is with so much luck that all the integrals involve Dirac delta functions, so they can be done by inspection. But please note the property of the Dirac delta function. So you have here this property you have to remember, and you're integrating a 4-dimensional quantity. So later on we'll see how it's integrated. So note that when you integrate a function with the delta function here, so you have to know that delta function of x is, or x, say if x is equal to 0, then this is infinite, and this is 0 when x is not equal to 0. The argument, so if the argument is like x minus x prime, then it's infinite if x is equal to x prime, and it's 0 if x is not equal to x prime. So when you have a function multiplied to the delta function fx, then the integral would just be f of x prime. The integral of delta x minus x prime dx is just so from infinity to positive infinity, this is just equal to 1. So as mentioned earlier, the reason the delta functions are in the amplitude is to enforce conservation of energy and momentum. So it's very important. So at each vertex, assign a positive sign for momentum entering and a negative sign for momentum that leaves the vertex. So for instance, as shown in the figure, you have positive P1 and negative P2 and negative P3 in this case. So the total momentum in the vertex here is P1 minus P2 minus P3. By the way, to have the conservation, this must be equal to 0. So momentum and energy are conserved and it does not change because of the interaction. This conservation is described by, as we have shown earlier, P1 must be equal to P2 plus P3, and this must be included as a direct using the Dirac delta function here, unless this is equal to 0, unless this is supposed to be not equal, x not equal to x prime. The delta function that enforces the conservation of energy and momentum at the vertex is shown in figure 7.9. Is now this one. By the way, there should be a factor of 2 pi for each component of P. And since there are 4 components of P, you have 2 pi to the 4th. So the value of the delta function is 1 when P is equal to, when P1 is equal to P2 plus P3, and it is when you integrate the delta function, it is 0 when P1 is not equal to P2 plus P3. It must be equal. Momentum and for momentum should be conserved. The direction of the arrows indicates whether the given line is for a particle or antiparticle and does not have anything to do with the direction of the momentum. By the way, I'm sorry about here. This is correct. I had to erase this one. So, for a line going to a vertex, the momentum is entering the vertex. Following the direction of time, which can be up from the vertex or right from the vertex, these lines leaving the vertex should be assigned momenta with minus signs. Conservation of energy and momentum is enforced at the vertex involving an internal line as well. So this is a figure, conservation of energy and momentum enforced at the vertex. So in this case, for figure 7.10, you have a boson B carrying away momentum Q. So you can write the conservation of momentum here as P1 minus P3 minus Q equals 0. So the delta function that will enforce conservation of energy and momentum at the vertex in figure 7.10 is this one. So for this case, for 7.11, the conservation of momentum here would be Q minus P2 plus P4. Therefore, this is equal to 0. Therefore, your delta function would be this one here. The delta function should be of the form here, written here. It's all momentum that enters minus all the momentum that goes out. But as you can see in figure 7. As you saw in 7.11, you have their Q equals a minus P2 plus P4 equal to 0. It's the same as P2 minus Q minus P4. That's why you write the delta function as that. Now let's construct the amplitude, the integral of the amplitude. So construct an amplitude from a Feynman diagram involves the following steps. First, I'll just read verbatim. Write down a delta function to conserve energy and momentum at each vertex and multiply these terms together. So if you have two vertices, then you have two delta functions. And then write down one coupling constant for each vertex in the figure, and write down a propagator for each internal line. That means the lines in between the initial and final particles or final states. And multiply all the factors together and integrate over the internal momenta. So we will see an example of that later on. The total amplitude m is the sum of all the amplitudes mi that can occur for a specific process with the same incoming and outgoing particles, no matter what the internal process is, for as long as the initial and the final particles, the incoming particles and the final particles are the same. Then you would have to assign it, or you have to include it in the sum, in the Dyson series. Each mi corresponds to a Feynman diagram. So the total amplitude for a process a plus a prime going to a plus a prime is the sum of the two amplitudes represented by 7.6 and 7.7. In fact, higher order diagrams for each of those processes can be drawn with different intermediate states. So let's look at 7.6 and 7.7 again. So we have the same incoming and outgoing. So here you have a prime as incoming and outgoing a and a prime, and then you have for here you have the same incoming and outgoing. In this case, you have an interaction, a scattering interaction, and here you have annihilation, then creation. So now we'll now go to the coupling constants, which is very important in each vertex because you have to specify the coupling constant for the vertex. So every force has some fundamental strength. For example, in QCD you have a strong force and it's represented by a coupling constant, which is, it's very complicated because it's greater than 1 for QCD. But for QED, which we will discuss, of course, all of them later on in the theory, in their corresponding theory. For QED, you have a coupling constant that is less than 1. And, well, of course, that's very helpful in perturbation theory, because as you go to higher order Feynman diagrams, it contributes less and less, which is opposite in QCD. So for QED or quantum electrodynamics, for example, the coupling constant is GE, and it's related to the fine structure constant alpha, and that alpha is just equal to 1 over 137. It is a dimensionless number with constants, charge, electric charge, speed of light, and Planck's constant h bar here. You can derive this number, so you can try it for yourself. So for QED, the coupling constant, which is small, less than, very much less than 1, then the higher order diagrams contribute less and less because they include higher and higher powers of G as you go to higher order Feynman diagrams. This means that the series can be terminated at a point where the accuracy needed to describe a given process is already obtained. So you can terminate that. So for each vertex in a Feynman diagram, include one copy of a coupling constant, which is given by this one here. You have to multiply a negative I. Now we will go to the propagator, which is associated with the internal line in a Feynman diagram. This is a factor that represents the transfer or propagation of momentum from one particle to another. The propagators for three types of particles that will come across later are given by, the first one is the simplest case, which is an internal line for a spin zero boson. This is the internal line. Where m there is the term representing the mass of the particle that corresponds to the internal line. In QED, we sometimes denote an internal line with this one. This represents a photon, which is massless, so its m there is 0. So you can we will explore that in later case. For a spin 1/2 particle, the internal line is indicated the same way as an external line. So it's a solid line with an arrow pointing in the direction of momentum for a particle and against the direction of momentum for an antiparticle. So usually for an internal line for a spin zero boson, you can just write it with a dashed line. And this is the propagator there. So for spin 1/2, the propagator would be this one. By the way, if you recall, slash q is just equal to gamma mu q mu. So here's the photon propagator, which is massless. So it's different looking, which this is complicated, but we can study further this one later on in QED. So we'll just look at this as the propagator. So the propagator of the photon will just be this one here in the Feynman gauge. So later on we'll explain this in QED. So recall the steps used to build up the amplitude from Feynman diagram. Take each factor and multiply them together as a product. Now write down one factor of Ig for each vertex in the diagram, where G is the coupling constant for the interaction, and then write down a delta function in general for each vertex to conserve momentum, and add a propagator for each internal line. The next step is to integrate over all internal momenta. So for each internal momentum Q, add an integration measure to enforce the normalization in the phase space. So you have to write this factor in the integral. Then integrate for each internal momentum, and in the end there will be a final delta function left over that enforces the conservation of energy and momentum for the internal lines. Then simply discard this factor, and the result left over is the amplitude for the given process. So this is very important. So let's now go to an example. Example 7.1. So for here, a particle A annihilates with its antiparticle A prime, producing a spin zero scalar boson which subsequently decays into A and A prime. The mass of the scalar boson is MB. Calculate the amplitude and probability for this process shown in figure 7.14. Let's go to the figure. By the way, looking at the figure, you have two vertices and one internal line. So as the rule says, but you have to write down a factor negative Ig for each vertex, and since there are two, so you have this. Negative Ig times negative Ij would give you negative G square. Next, multiply this by the Dirac delta functions that will conserve form momentum at each vertex. So as you can see in the figure, you have for this vertex you have you have 2 pi to the 4th P4 minus P3 minus Q. And for this vertex, you have this one. This here. By the way, this is positive. This is positive. And for P2, P1, you have P1, P2, you have this one. This arrow is, by the way, just telling you that this is an antiparticle. So so let's go back. This is actually equal to, the delta function should be negative P4 minus P3 plus Q, because only Q is incoming to the vertex at the top. And then at the vertex below, you have P1 plus P2 minus Q. And so, by the way, this one is also minus, and this one is minus. So the next step is to add a propagator for the internal line, and since the spin is 0 because it's a boson, boson could be like a photon is a boson, so it's spin 0, then we multiply everything, the delta function, and this one is minus, so we will have this quantity. Now we integrate over Q using the measure. So we have to multiply this before we integrate. And this one, this 4 pi will cancel with this 4 pi. And this is dq to the fourth. So this integral can be done by inspection. So you will be left with one integral after the integration. So this is now you can use this, so that this is 4. So you have this one, and Q would be equal to this one, and that your this one will be the integral left after the integration, and you can discard this after the integration, but let's just put it there first. So you have that as your amplitude. So the above integral, there is supposed to be 2 pi to the fourth here, P1 plus P2 minus P3 minus P4, but you have to discard this, so that you're left only with this one. You're only left with this one as your M. So the probability for a process to occur is the modulus squared of M. That is this one here. This is proportional to the process occurring. The probability of the processes, the process to occur. And this is also proportional to the cross section as well. Now let's go to example 7.2. For this next example, a particle decays as follows. U decays into W and V with a coupling strength of GW. The particle W then decays into W, decaying into V prime plus E, or this is a neutrino, an anti-neutrino plus an electron, with a strength given by the same coupling constant. Draw the Feynman diagram for this process and calculate the amplitude for it to occur. The W particle is a spin zero boson with mass MW. So let's look at the solution for this example. So this is the Feynman diagram, as you can see. Sorry, the pen lost its color. So here you have a U decayed into nu and W, and then the W decayed into an anti-nu and an electron E. So there are two vertices, and you have an internal line which is a spin 1/2 particle, the boson, because this is a dashed line. So let's look at now the amplitude. So let us now look at the amplitude of the Feynman diagram, but before that, let's clean this one here. So you have the first vertex here, this one. You have P1 coming in and P2 going out, and the Q. So your direct delta there would be this one, and of course you have a factor of 2 pi to the fourth, and then you have two vertices, and that would give you negative GW square, and then the particle W decays into the final product. So it is represented by an internal line, and the propagator is given by this one, and the second vertex there is an incoming momentum Q and an outgoing momentum P3, and then P4. So you will have this direct delta, or this one here. So if you multiply together, putting everything together, so you have the vertex, the second vertex, the first vertex, the internal line, and the coupling constant, since there are two vertices. And we now integrate. We multiply this one, and this one will cancel with that, and so we're left with I G W square pi to the fourth, and then when you integrate with the Q, then you can use this Dirac delta and substitute it here. So that's why you have this one. That's why you have this one here. And then your Q will be P3 plus P4 minus MW square. So we have to cancel this one in the final expression of the amplitude. Of the amplitude. So this one should not be there. We have to drop that. So that's the amplitude, and then you square that. That would be proportional to the probability of occurrence of that process. So other important quantities that can be found in the Feynman diagram are the rates of decay and lifetimes. And the decay rate is proportional to the amplitude, the square of the amplitude. And the lifetime is proportional to the inverse of the amplitude. So, as a summary, Feynman diagrams allow the representation of the amplitude for a process to occur with a picture, and that is the Feynman diagram. And external lines represent incoming and outgoing particle states, and at each vertex, conservation of energy and momentum is enforced with the delta function, and the strength of the interaction is included with the coupling constant. And then internal lines can represent force carrying particles or particles that spontaneously decay into the end process, in end products. Each internal line is accompanied by a propagator that represents transfer of momentum to the final states, but the propagator there should be noted, because it could be a spin 0, a spin 1/2, a boson, which is integer spin, or half an integer spin. So they have different expression for the propagator. And even so, if you have a boson and it's a massless boson, then the more that the mass is 0, so it's another expression. So that's it, guys, for this lecture, and this chapter is finished, and so we'll proceed with the next chapter. And I hope that you've learned something in this lecture.